so let's continue. So basically what we have seen is that if you define a robot like this, okay, then there is a base of the robot which does not move. So we are making the assumption here that the base is not moving, okay, and only the end effector is moving. Okay. So only our end effector here is moving, and the base of the robot is fixed, it is not moving. Okay. So basically what we need to know is relation between the position orientation of this last end effector with respect to the base of the robot, right. So if I draw it again here, this has got a little clumsy. Okay. So basically what we are trying to say here is that we have a linkage mechanism like this, okay, and what I want to know is what is the relation of the end effector with respect to the base frame. Okay. That is what I need to know. So let me draw this again, this has got very messy. Okay. So I have my end, the base point here. So I have one link here, one link here, one link here, like that, number of links. So I need to know the position orientation of the end effector with respect to the base frame, which is not moving. Now how do we know that? Basically I have to assign frames to each of the joints. Okay. So to the base joint I assign my frame 0, Z0 and Z1, which is not moving. My X0 is here, X1 is here. This is my Z axis, X2, Z2, sorry, this is X2. This is Z3 and this is my X3. Okay, I have assigned frames to each of the joints. Now, when this is moving in space from the full hand, I need to know the relation between this axis which is the origin there, with relation to this axis, and then from here to here, and from here to the 0 axis. Okay. So what we do is we assign our 0 frame to the base which is not moving. Then to the first axis I assign frame 1, then I assign a frame 2, then I assign a frame 3, I can also assign a frame 4 there, okay, an axis. Frame means an axis. Okay. So basically the idea being that I need to know the relation between this axis and 2, then from 2 to 1, then from 1 to 0. So if I know that, then I know the relation between 3 and 0. So when the robot is moving around in space, the position orientation of this one is changing with reference to the 0 frame always, right. So I need to have some relation between this frame and the previous frame, this frame and the previous, in that order. Now if you see the relation between the 0 frame, so my X0 is here, Y0 is here, Z0 is here. So if I look at the relation between that frame and this frame, then you see that this may have a rotation angle, it may have an angle, the X3 and the X0 are not in the same direction. So there is an angle between this X and that X. Similarly, there is a distance between this origin and that origin there. Okay. So two transformations are involved. One is called the rotation transformation, which gives the relation between the orientation of the last frame with reference to the base frame. Okay. So one transformation is the rotation transformation. The second transformation is the translation transformation, which is the distance between the origin of here and the distance of the origin there, right. So essentially this is saying that if you want to go from any frame to any other frame in space, then at most we need one rotation transformation and one translation transformation, only two are required. Okay. So from here I can come here, then from here, 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 in that order, irrespective of how many links are there. Okay. So we need to look at the rotation transformation, which relates the angle between two frames, and then the translation transformation, which relates the origin distance between two frames. Okay. Now I said that I fixed an axis, my x axis, y axis, z axis at joint number 0, then 1, 2, 3. So what is an axis? An axis is a direction in space. Okay. So an axis by definition is the direction in space. How many axes? Depending on the space you are in. If I am talking of 3-dimensional Euclidean space, then it is 3 axes, because in Euclidean space we have 3 axes. If you go to higher dimensional space, then there can be n axis. Okay. Hyperspace has n axes. So depending on the space you are in, you will define that many axes. Now in 3D Euclidean space, we are defining 3 axes, 3 directions in space, x, y and z. these three directions are orthogonal to each other. We are defining it like that. Okay? And so this is my 3 axis I am defining, my x axis, y axis, z axis as per right hand rule, okay, plus the axes are orthogonal. The axes are, each of them is a unit vector, okay, plus the axes are orthogonal. Okay. So, we are fixing the axis. So, it is up to us. Now, I have fixed 3 axes, I mean 3-dimensional Euclidean space as x axis, y axis, z axis, and these are orthogonal vectors and they are unit axis, unit vectors. So, each of this is I, j and k, they are unit vectors which are orthogonal to each other. Now, in this axis system, I am going to define the position of a point. How do I do that? I put a point here and say that the position of this point is x, y, z. What does this mean? This means that if I take a projection from P and put it here, this will be x, this will be y, and that will be z. That's the meaning of coordinate of a point. So, how do I define the coordinate of a point? A point has coordinates which are the projections from that point onto the respective axis. And that is my x into I plus y into j plus z into k. I, j, k are the unit vectors. So, a position in space, a point in space has only position, it has no orientation. Okay, a point cannot have orientation, it has only position. Now, positions are in the axis system which we have fixed as x, y, z as per right hand rule like this. So, when I am saying x, y, z, I understand what I mean by x, y, z, right. Now, we also saw that there are other conditions, these directions are unit vectors, they are orthogonal to each other. Okay. Why? Because I have put my axis like that. Now, let us move on to trying to figure out the rotation between 2 axes now. So, in order to find out so a point has position, no orientation. Now, if I talk about the orientation of a rigid body, then how do we define it? So, what we do is we have one axis which is fixed here, which is not moving. Now, if this is my rigid body like this, okay, and this is my axis system. So, what we will do is I will fix one more axis here. Okay, so, one axis here now, like this, and now say that what is the angle between this axis and this axis now. Okay, and now say that this position is x, y, z of this point, plus it has 3 more, which is the orientation of this body, which is defined with respect to the angle between the x axis, y axis, z axis of this body versus the x, y, z of this frame now. Okay. So, for a point we have position, no orientation. For a rigid body we have position and orientation. Position of which point? Position of any point on the body. Normally we say CG of the body or here. Okay. So, this body has this position has x, y, z coordinates. We know what is x, y, z with reference to this frame. Now, it also has an orientation. What is the orientation? It is the angle made by the x, y, z of this fellow. Let us call this x, y, and z with reference to this x, y, and z. That I call the orientation of the body now. Okay. So, we understand what do you mean by position and orientation of a body now in space with reference to the base frame. So, the first transformation that we have to look at is the rotation transformation, and for the rotation transformation we need to find what is the angle between the corresponding axis, between this axis and that axis now. How do we do that? Let us start off with a very simple system in which I say that my base frame here is x, y, and z as per right hand rule. This is the frame which is let us call it frame A or frame 0 which is not moving. So, this is my frame 0 or frame A which is not moving. Now, initially let me say that I have another frame which is this frame. Okay. So, there is another frame, frame B. This is my frame B. Okay. Now, initially both the frames, frame A and frame B, are the same frame. What is the meaning of same frame? It means the origins are the same and there is no angle between the x, y, z of B. That is the meaning of same frame. Okay. So, initially I am saying this frame A and frame B are the same frame. Okay. Now, let me say that I take my frame B, I rotate my frame B by some angle. So, I rotate my frame B, it comes here. Now, I say I take my frame B and I rotate it with an angle theta about the z axis of frame A. So, this is my frame B now, it has rotated, the origins are still the same, but frame B has rotated and has gone there. So, the x axis of frame B is here, the y axis of let us call this x dash and y dashed of the two frames have gone, x dashed is here, y dashed is there. Okay. Now, there is an angle theta between them. We rotated about the z axis. So, there is no there is no change in the z axis. Why? Because we are rotating about the z axis. Okay. So, what did we do? We had two frames A and B which were the same frame, origin were same, there was no angle. We rotated this by angle theta. Now, it has gone here, x is here, y is there, z is the same. Now, I have a point here. Okay. This point, let us call the point P. Now, it has a coordinate in frame B which is given by UVW. Okay. What is UVW? Now, in robotics, whenever we write a point, you also have to write the frame. Okay. Why? Because there are different frames now. So, if I say P, P is the point and the frame is B, its coordinate is UVW. What does this mean? That the projection here, the projection on this is U, that is V. This is my U, that is my V. Sorry, this is my U, not that one. Okay. So, this is my U and that is my V. This is what it means, UVW. What is W? W is in the z direction. That is the meaning of UVW. Now, this point has a coordinate in frame B. It also has a coordinate in frame A. So, if I say my coordinate in frame A is PA, then its coordinate is x, y, z. Okay. So, I have a coordinate, the point is the same point, it is point P, but it has different coordinates in two frames because these frames are rotated now. So, on UVW, this is U, that is V and that is W, x, y, z, my projection is going to become x on the x axis. So, it is here, this is my x, that is my y, that is the meaning of x, y, z. So, I basically want to find the relation between x, y, z and UVW. Okay. So, this relation will give me the transformation or rotation between this frame and this frame. So, the rotation matrix gives me the relation between a rotated frame to that of the reference frame. Okay. So, what I am going to do, the base frame is not going to move, I will fix the frame onto the next link which is moving, and when that link rotates, I basically need to find the correlation between the rotated frame and the reference frame, and that is the rotation matrix now. Okay. So, the first transformation is a rotation matrix. Now, geometrically, let us look at how do we derive that. It is very simple. If you look at the figure geometrically, if I make this small construction here, okay. So, this is my construction, okay. And yeah. So, let us look at this construction and try and figure out what is the relation between x, y and z. So, let me write x here. So, x is equal to, this is x, this distance is x, right, the projection of that on the x axis is x. Now, this is equal to how much? This is equal to this full length minus this length, right. So, if you look at geometrically, x is equal to what? This is my x. So, it is equal to this full length from here to here minus this length here. Okay. So, this x from here to here is equal to this full length minus that much length, right. So, how much? So, I am writing x here, that is x. How much is this one? This is equal to u, this is cos theta. So, it is u cos theta is this full length. So, I am going to write u cos theta, okay. U cos theta I am writing in short, u cos theta is this length minus this much. How much is this much? This much is equal to this much, it is a rectangle, right. So, this length is equal to this length, it is a rectangle, and how much is this much? So, this angle is also theta, because if this is moving by theta, that is also theta now. Okay. So, if this is theta, this one is v. So, this distance is v. Okay. So, how much is this length now? So, if this is theta, that is v, then this is equal to v sin theta. Okay. That means, if this is v sin theta, this is also v sin theta. So, if this is equal to x, x is equal to u cos theta minus v sin theta. So, it is u cos theta minus v sin theta. Okay. So, geometrically we can very easily define what is x in terms of the rotated system. Okay. What about y? Y is this distance. What is y? Y is this distance. Now, this distance is equal to this distance plus that distance. Now, this distance is equal to how much? This is u and this cos theta. So, this distance is equal to this distance. So, it is u sin theta, and this distance is equal to v, is equal to this distance, right. So, how much? Let us do this one first. So, this is equal to this much. So, this is equal to u sin theta. So, this is u sin theta. Okay. So, this much is equal to this much. So, is equal to u into sin theta, which is this much. What about this much? This much is equal to this much. Okay. So, this is equal to v cos theta plus v cos theta, right. So, geometrically we can derive the relation of the coordinate of a point expressed in a rotated system to that of the reference system very easily, simply by looking at the geometry. Now, we have x and y, x is equal to this, y is equal to that. What happened to z? Z will be equal to W, because it is not rotating about the Z axis. So, it is x, y and Z, right. So, very easily we can write x, y and Z like that, right. So, we have been able to find the rotation matrix. So, what is the rotation matrix? If I write it in matrix form, then the rotation matrix, I hope you understood this, right. All you need to do is to do it by yourself once, okay, and it will become very clear what is this matrix. There is nothing to remember and do all that. If you know how this is coming, you know very easily how that is coming, okay. It's very, very easy. All you need to do is to draw it once by yourself and then solve it, okay. So, if I write it in matrix form, then I can write this as x, y, z, x, y and z on the left hand side, x, y and z on the left hand side is equal to cos theta minus sin theta So, cos theta minus sin theta and sin theta cos theta 0 0 1 0 0, and on the other side we have u, v and w. So, I am writing this in matrix form. Okay. The same thing on the left hand side you have x, y and z, then you on this side you have u, v and w. So, I am writing it here, and this matrix that I am going to get is cos theta minus sin theta cos theta, and that remains as 1. Okay. So, if I write this in matrix form, it will come out like this: cos minus sin cos, this is 0 0 1, this is 0 0 0. Okay. That means, if I am given the coordinate of a point in a rotated system, I simply need to multiply it with this matrix and I get it in the reference system now. Okay. That means, I can rotate an object by some angle, find its coordinate in the rotated system, multiply it with this matrix and get it in the reference system now. Okay. And this is cos sin cos. Now, this is a very, very simple matrix. Okay. And if you note a couple of things here, this is a column vector, this is a column vector, this is a column vector. Now, these 3 column vectors, the mod of this is 1, 1 and 1. So, cos squared plus sin squared is 1, sin squared plus cos squared is 1, and this is also 1. Okay. Now, why is it like this? It is like this because that is the way we chose our axis. Okay. Please correlate this. We chose our axis as unit vectors which are orthogonal to each other in 3 different directions. Okay. Because of which this is a unit vector, this is a unit vector, this is a unit vector. So, it essentially means this column is unit vector, and unit vector. This corresponds to x axis, y axis, z axis. What does it mean? A little bit more intuition is the first fellow. Let me write it here, you can understand this better. So, this is the matrix is written like this. So, this is cos theta minus sin theta cos theta 0 0 1. This is the rotation matrix. Now, please try to see what does this mean in terms of this rotated system. It means the projection of the x axis, rotated x axis on this x axis is a cos theta. That is the meaning of this unit vector. So, this is a rotated axis, the projection of the x of the rotated projection on this is a cos theta. Okay. Projection on the y is a sin theta, and there is no projection on the z, so it is a 0. Okay. So, it will be 0 0 1, this will be 0 0 1, right. So, it basically means this column corresponds to the projection of the rotated x axis on this x, on that y and on the z. That is a cos, sin and a 0. What is the meaning of this column? It means the projection of the y axis, rotated y, on this x. So, if I see the projection on x, what is the projection on x? Projection on x is here, x is on the negative side now. So, if I take the projection here, it comes here. So, it becomes a minus sin theta, which is this much. This is my theta. So, there is sin theta, which is here. Okay. So, sin theta, projection on y is a cos theta, which is this much, which is here. There is no projection on z, so it is a 0. Okay. So, we need to very nicely understand the physical meaning of these matrices. Why in robotics? We need to understand when a physical body moves in space, as we just saw when we talk about degree of freedom of picking up something. I need to correlate the degree of freedom with an axis now. Okay. So, I need to understand this very, very clearly, and it is very easy. Geometrically, if you derive it, it becomes very clear how this is happening. Okay. So, this is my x axis, y axis of the rotated system. It is rotating about the z, so there is 0 0 1 there. Okay, because it is rotating about the z axis, so it is 0 0 1 rotation about the z axis, right. So, if I look at the rotation matrix, then this is the rotation matrix, cos minus sine, sine cos 0, 0, 1, u, v, w is on this side, x, y, z is on this side, right? So it's very simple. Now the way we derived it, I rotated about the z axis. You can also rotate about x or you can rotate about y, and we can derive it exactly the same way, okay? So here I rotated about z, you can rotate about x, and you can rotate about y. So in that case, what we can do is I can do the similar geometric construction and get the rotation about x, y, and z. Z I have done, x, y you can do that, okay? So if I rotate about the, so the way we write it, so the way we write this is we write the rotation matrix as r z theta is equal to the rotation matrix. Now the way of writing in robotics, if you refer to the textbook or any book, it is always written this way. This is the rotation matrix R. It is rotated about the z axis by an angle theta. This is the meaning, okay? So it's cos theta sin theta, it is this matrix. So it is cos theta sin theta cos theta, okay? Now if I rotate about the x axis or the y axis, then what will happen is rotation about x axis, rotation about the x axis is, if I say x theta, then what will happen is essentially you are now rotating about the x axis. So if you are rotating about x axis, there is no change on x axis. So it will remain as 1 here, right? So this part is automatic. Why? Because here we rotated about z axis. So if you are rotating about z, this fellow will become 1, it will become 0, 0, 0, 0, rotation about z, okay? Now if you are rotating about x, then what will happen is this will become 1, 0, 0, this is 0, 0, this is cos minus sine, so this becomes cos minus sine, sine and cos. So if you note the terms cos minus sine, sine and cos, then essentially what is happening is if you see cos sine, sine cos, here also it is cos sine, sine cos. So those 4 terms have only changed position, nothing else has happened, okay? So there are only 4 terms, there is nothing to remember. And if you derive it by yourself once, please do derive this once today after you go back home in the evening. It will become very clear how this matrix comes. And you just need to remember that there are 4 terms only, okay? Now if you are rotating about x, if you are rotating about y, then what happens is this becomes r y theta. So rotation about y will mean that this term will remain as 0, 0, okay? So what will happen? Only you will become cos minus sine, sine cos, okay? So if you are rotating about y, this will become 1 because this is a rotation about y axis, okay? That this 4 fellows will just change their positions, that is all, nothing more will happen. So now you can rotate about any axis and you have the rotation axis, which is very, very simple, okay? So the mathematics is not scary once you understand it, it is very, very easy actually, okay? Now we can rotate about 2 axes or 3 axes simultaneously, okay? So first I could have rotated about the x axis, so I rotated about the z axis here, I rotated, it came here. Now I can rotate about the x axis. Now if I rotate about the x axis, what will happen is I am rotating like this now, okay? So what will happen? B will go that side, x, y and z has come this side now. If you can imagine, I first rotated about z, then I rotated about x. So what will happen is now the b axis has gone there, okay, after 2 rotations. So the first rotation is about z, then the rotation is about x. Now so now what is the relation between the coordinate of the point P with respect to this axis? There are 2 rotations, about z and about x, okay? So what you do, you multiply the 2 rotation matrices, one about z and one about x, okay? So it's very simple. So once I rotated about z, this is the rotation matrix. Next I rotated about x. So in that case, this is the rotation matrix, okay? So I simply multiply those 2 matrices and get my combined matrix. Now something to remember here is that when we are multiplying 2 matrices, 2 rotation matrices, you need to pre-multiply, okay? Why? Because these are matrices, so A into B, so A in A is not equal to B into A, okay? So so because these are matrices, so A cross B is not equal to B cross A, okay? So the order of multiplying is important now, okay, because these are matrices now. So if you are multiplying 2 matrices, 2 rotation matrices, then what we say is we pre-multiply. So, please remember this, you have to pre-multiply the matrices when you are multiplying. So, here it is please remember this, that you have to pre-multiply the matrices. So, first if I am multiplying, say r z theta is my first rotation, if my second rotation is rx, let us say psi is my second rotation, okay, then in order to find the combined matrix, what I will do is I will pre-multiply, so it will become, so this is 1, this is 2, so it will become rx psi into r z theta. Okay, this is the meaning of pre-multiplying. So, I first rotated this, then I rotated this. But when I am multiplying and finding the combined rotation matrix, then I pre-multiply, this one comes first, then this one. So, I am just reversing the order. Okay. So, this is called the pre-multiplication of matrices. Okay. Now, please remember this, that you need to multiply, pre-multiply. Yeah. Yeah. So, what is the physical significance of this? Now, how did this fellow go here? First we rotated about here, so from here it went there. Then what did we do? It went there, it went here. So, this is my first rotation, second rotation. Now, if I want to bring it back and aligning it with this, then what is the order I must follow? So, this was my first rotation, then this was my second rotation, right. So, this is my first rotation, and then it is my second rotation. And then this is my second rotation, right. So, this was first rotation, this was the second rotation. So, now if I want to align this with this, I must first do this one, then I must do that one. So, the order is reversed. Is it okay? Does this convince you that the order reverses, right? Why? Because it has gone first about from here to here, then it has gone from there to there. So, what we will do is to bring it back, I will bring it back from here to here, then I will bring it back from there to there. So, the order 1, 2 has become 2, 1 now, right. Now, there is a more interesting example, is when you put on your socks and then your shoes. So, when you reverse it, you first take out your shoes, then you take out your socks, right. If you put on a sweater and a shirt, you put on the shirt first, then you put on the sweater. But when you reverse it, you will take out the sweater first, then you will take out the shirt, right. And it is exactly because of this only, right, because in the real world this shirt and sweater and socks and shoes is rotations in space in real world. So, rotations in the real world, they pre-multiply, okay, irrespective of what you are doing. Okay. So, all rotations in the real world, you have to pre-multiply. Okay. So, the reason is I just explained that you first do this, then that, but then reversing it, you do this, then you do that. Okay. Now, please remember that you have to pre-multiply the matrices. Okay. So, we pre-multiply the order means you reverse the order. Please remember this. Okay. Now, of course, you can also rotate about the rotated system. Here I am rotating about the reference frame. This is reference frame, that is reference frame. I can also rotate about the rotated frame. That means after it has rotated there, instead of rotating about this, I can rotate about that. Okay. I can do that also. In that case, you do not pre-multiply, but the order remains the same. Okay. But this part is a little confusing. So, in robotics, we do not do that. Okay. So, robotics, we do not normally rotate about rotated frames. We always rotate about fixed frames. Okay. And just remember that it can be done, in which case the order remains the same of multiplying the two matrices. So, we will be following this method of pre-multiplying the matrices whenever we are following rotations, okay, and you are rotating about fixed frame. Pre-multiply about fixed frames. So, whenever we are saying pre-multiply, it is about fixed frames. Okay. So, now next is we talked about the rotation matrix. Now, we have to talk about the translation also. So, we have two frame. Okay, before I go on, the other properties of this we need to understand very clearly. So, let us so this matrix we need to understand the properties very clearly. So, understanding the properties of this matrix is very, very important. One we have seen is that if this is my x dashed, y dashed, z dashed, then mod of x, okay, is equal to mod of y is equal to mod of z, right. So, x, y, z, the mod of x of this is all equal to 1. These are unit vectors. Next is that if these are unit vectors, okay, if these three fellows are unit vectors, then the determinant of this matrix R is also equal to 1. Why? Because they are unit vectors. Okay. So, this matrix, the rotation matrix, has a structure such that these mods are all equal to 1 and the mods are equal to 1. The determinant is also equal to 1. Okay. Now, if the determinant is equal to 1 and the mods are equal to 1, then this matrix is a proper orthonormal matrix. So, this is a proper orthonormal matrix, and for a proper orthonormal matrix, the inverse of this is equal to the transpose. Why? Because the determinant is equal to 1. That means the inverse will be adjoint of A by the determinant of A. Determinant of A is equal to 1. So, which automatically means that the transpose is the inverse, right. So, this matrix has a lot of properties. It's the unit, these are all unit vectors, okay, they are equal to 1, determinant is equal to 1, because of which the inverse is equal to the transpose, and this is called a proper orthonormal matrix. Now, similarly, this is also proper orthonormal, and these are all unit vectors, okay, that holds. Now, let us look at the second part is I want to find the relation of a frame which is rotated and translated, both. In the previous case, the frames were only rotated, they were not translated. So, both the frames were rotated about axis, but the origins were the same. Now, I am rotating and I am translating. So, what would happen is, if you can imagine this fellow and this origin is the same first, there is no angle between them, they are all the same axis. Then I translate this fellow from here to here and I rotate it by some angle. Okay? So, there are two frames now, frame A. So, frame A, which is here, and frame B, which is there. Okay. Now, frame B has been translated, means the origins of these two are different now, and plus it has been rotated by some angle. Okay. Now, the coordinate of a point P, this is a point P, in frame B is given by UVW. What is the meaning of UVW? The projection on this frame B is U, V, and W. Now, the projection of this point in frame A is x, y, z. So, if I say this is my x, that is my y, and this side is my z. Okay. So, now we have the point P, which is the same point, but there are two frames. This fellow is not moving, it's fixed. This guy has rotated and translated, both it has done. Now, I want to find the relation between this matrix, between the coordinates of a point UVW and x, y, z, and I find it like this. So, this is my UVW. So, U is this, V is that, and z. Similarly, this is my x, that is my y, and this is my z. Okay. Now, if I look at this equation, if I look at this vector diagram, then what I want is this vector. Okay. This vector essentially is x, y, z in frame x, y, z. Okay, that is this vector, right. So, what is this vector equal to? This vector is this one plus that one. Okay. So, in terms of vector diagram, what is the meaning of coordinate of a point again, if we go back again. So, when we are saying the coordinate of a point x, y, z, we basically mean this vector. So, when we are saying coordinate of a point, what we mean is this vector, right. So, x, y, z essentially means I am connecting this to the origin, and this vector is x, y, z. Okay, this is the meaning. So, if I now connect this vector here to the origin, then what I want is this one, and this is equal to this one plus that one. Okay. So, if you look at the vector diagram here, then this vector AP, if I write AP here, so if I write AP here, then AP is equal to, so APB, this is the way it is written, and this is my BP. So, in terms of vector diagram, closed vector diagram, this is APB ORG, meaning AP is the point P, A is the frame A, and B is the frame B. So, PAB means the origin distance. So, it is written APB ORG, means the origin distance between two frames A and B is given by this vector. Okay, this is the way it is normally followed. This is the convention of writing. So, we have two origins, one origin here, another origin there, and the distance from here to here is given by this vector here. So point P, distance between origins of frame A and B, ORG stands for origin. This is the vector AP, means point P expressed in A is called AP, so it's this vector. This is BP, so point P expressed in B is this vector. Okay, so we have this plus that is equal to that from vector diagram, right? So I can write it as AP is equal to APB ORG plus BP, okay, in terms of vectors. Okay, did you follow how this axis went there? Is that clear? Huh? Translation and rotation. Rotation is also there, translation. So there is also an angle here. Let's say there is an angle there. Okay, so it has rotations and translations. Rotations are same as this. Okay, this is rotation is very clear. What is rotation here? So you are rotating about an axis. Now I am also translating the origin. So translation and rotation both it has. Okay, so I want to find this relationship. Now in this relationship, AP is equal to APB ORG plus BP means this vector is equal to this vector plus that vector, right? It is the distance between the origin of this frame and that frame, the amount it has translated. Okay, so the amount it has translated is from here to there. So this is my APB ORG. Okay, so it has both rotations, is the rotation about the angle, that is theta, and it has a translation, which is the motion from here to there, right? So this is having a rotation and a translation, and I can write it in this form. Okay, now this vector equation, is it correct, or anything more is required? Is this vector equation correct, or is not correct, or you need to do something else? Multiply by what? Multiply with what? No, why multiply? So we cannot add vectors in different frames. So whenever we add vectors, they have to be in the same frame, right? They must be aligned. They can't have a rotation between them. Otherwise, you can't add vectors, right? So now we have two frames, and these two frames have an angle between them. So when we are writing like this, they have to be in the same frame, same orientation of the frame. So how can we make the same frame orientation? I put a rotation matrix there. So what I'll do is I'll put a rotation matrix here, and this rotation matrix will be, so this is my rotation matrix AB, and this rotation matrix will convert it into the same rotation now. So this is also rotated in the same frame as that. Now I can add. Okay, have you followed this, how this equation came, right? So you just have to follow. There is nothing difficult here. Okay, so there is nothing difficult in whatever maths we are doing. It's, you just have to understand, that's it. And this is geometrically done. Okay, so there is no advanced maths in that. So now this, now I can write this as this plus that, and this will be written in the form of, so this is my x, y, z 1. Now this matrix is a 4 by 4 matrix. This is u, v, w 1. Okay, and this is my, the distance between the origins is here. I call it del x, del y, and del z. So this is del x, del y, and del z. This is always 0, 0, 1, and this is always my rotation matrix. Okay, so this one is a 4 by 4 matrix. Okay, so the rotation matrix is 3 by 3, which stays here. So this is my 3 by 3 matrix, which is same as the previous one, cos, sin, sin, cos. This is the distance between the origins, which is this one. So this fellow is here. Okay, so this fellow is here. Okay, so this ABORG is this one, the distance between the origins. So distance x, y, and z, which is here. This is the rotation matrix. This is always 0, 0, 0. This is always 1, and this is UVW in the rotating system. Okay. Now this is a 4 by 4 matrix called the homogeneous transformation matrix. You'll be using this matrix only because it takes care of both rotation and translations. Okay. So we'll be using this matrix only, and it's very easy to derive. First derive the rotation matrix, then derive the transformation matrix, and if you combine it like this, then we can write it in one matrix called the homogeneous transformation matrix, which relates the position and orientation of a point in a rotated and translated system to that of the reference system. So, this is rotated and translated system to that of the reference system. So, this is a 4 by 4 matrix. This is always 0, 0, 0, this is always 1. Okay. Now, yeah. So, now something again important here is that this is called the rotation part, this is called translation part, this is called perspective, and this is called scale. Okay. So, this has 4 parts and it has 4 names. The 4 names are so the 4 parts of the matrix, this is called the rotation matrix, okay. This is called translation, this is called scale, and this is called perspective. Okay. So, there are 4 parts of this matrix and 4 parts have 4 names. This is the rotation matrix, this is the translation part. Translation means translation of between the origins, distance x, y, and z. This is the perspective. Okay. Perspective means this is always 0, 0, 0, this is always 1. So, in robotics, this is always 0, 0, 0, this is always 1. Okay. Now, we will do a very simple problem, it will become very, very clear, okay, how this works, but there is a lot of understanding of this, like the rotation matrix. We saw the rotation matrix in the real world also is a rotation matrix, right. So, in the real world, how is this 4 by 4 matrix? Why is this 0, 0, 0? Why is this 1? Okay, that is also important to understand. Now, if you go back and think a little bit, we can think about the rotation matrix, how we got it, and the rotation matrix came out to be 3 by 3 matrix. It is a 9 equation matrix. Now, the rotation matrix has 9 elements, 1, 2, it's 3 by 3, so 9 elements. Now, in the real world, although this has 9 elements, you do not need 9 parameters to define the rotation of an object in space. Okay. Please listen to this carefully, that this matrix has 9 elements, it's 3 by 3, but it does not mean that in the real world you need 9 parameters to define the rotation of an object. You need only 3 parameters. What are those 3 parameters? Angle between the x-axis, y-axis, and z-axis. Right. Now, why is it like that? It's more important to understand. Now, it is like that because although this has 9 parameters, they are not independent parameters, they are dependent parameters, because they are related like this. So, the parameters are not independent. Otherwise, to define the rotation of a body in space, you would actually need 9 parameters. You don't need 9, you need only 3, the direction cosines. Now, it is like that because although there are 9 parameters here, this fellow has 9, but we have 3 of them here. The other 3 is x dot y is equal to y dot z is equal to y dot x is equal to 0. X dot y, y, z, and x, z, sorry, x and z. Okay. So, we have three equations here, 1, 2, 3. We have another 3 equations there, this, and that. Okay. That means there are 6 dependencies, although this has 9. So, 9 minus 6 is 3, and that is why you have 3 independent parameters. Okay. So, this is all happening because we set our axis like that. Now, going a little bit forward, in our homogeneous matrix, we have 4. So, why is it 4? Because in 3D Euclidean space, so we are talking of 3-dimensional Euclidean space. In 3D Euclidean space, you have only, so 3D Euclidean space, you have 3 parameters only. What are the 3 parameters? X, y, and z, right? You have only 3. So, these 3 parameters are taken off by the rotation matrix. You don't have any more parameters. So, you cannot do translations in Euclidean space. You have to go to some other space. So, that space is what we call homogeneous space. So, I take a point x, y, z in Euclidean space and I scale it and put it in 4D space and w. Okay. So, what are we doing? I take a point in 3D space x, y, z, multiply it with a scale parameter and convert it into 4-dimensional space. This is 4-dimensional space. This is called 4D homogeneous space. Okay. Why? Because in Euclidean space you have only 3 parameters and those 3 are gone. So now I need to take another 4 parameters. I need to convert from 3D to 4D by adding a scale parameter here. Okay. Now again, like wearing shoes and socks, which you do every day, okay, or wearing shirt and you do these translations in the real world every day. So this kind of transformation, where do you do? You do this almost every day. Where have you done this kind of transformation? You have gone from 3D space to 4D space and you have come back again. So all these things that we are some amount of mathematics, but then in the real world it is valid because we are also linkages, we are in the real world, right? So this going from 3D space to 4D space and then coming back, where have you done this? You do it very commonly. Where? You have gone from one space to another space. Of course, there is things like when you're dreaming, you're in dream space, but this is not dreaming. You're going from one space to another space, from 3D space to 4D homogeneous space. This is 4D space. And then you're coming back again. Huh? Light? Flight, you're in 3-dimensional world. You're in XYZ only. In? Where in graphics? Where? When? That is rotations only. Something a little bit which is commonly done, but you might not have noticed that you're moving between spaces. That is in 3D world. Real world is 3D. Okay. Real world only has 3 dimensions, X, Y, Z. Of course, some people tend to believe they live in other dimensions, but okay. Let's leave that now. Where exactly? So in computer graphics or using any software like Word or PPT, or when you're using a software to look at a picture, okay? When you use the zoom function, what does it do? It scales it, right? When you're using that zoom, either to make it bigger or make it smaller, is it creating another picture? Then what is it doing? So when you're looking at a picture on your mobile phone, on a laptop or something, you zoom it, the picture becomes bigger. Then you make it smaller, it becomes smaller. Is it creating another picture? No, then what is it doing? So what it is doing is exactly taking these coordinates. Okay. So it is exactly taking the coordinates in 3D, multiplying with a scale parameter, and then making it bigger. Are you following? So from the 3D it is going to 4D by changing that scale. Okay. So if it makes it more than 1, it will become bigger. If it makes it less than 1, it will make it smaller. The coordinates are exactly the same, right? So this is called the scale parameter, and what the scale fellow does is essentially it is doing, it is scaling. So it is scaling between from 3D to 4D. Now in robotics it is 1. Why? Because the link length should be the same length. Otherwise the link length will become bigger or smaller. That we don't want. Okay. So in robotics it is 1 always. In computer graphics, in image processing, all that, this scale parameter changes. In computer vision, when you're taking a picture, okay, what is happening again is, if I take a picture of this room, this is 3-dimensional world, X, Y, and Z. But in the picture, it is only 2D. It's X and Y. Your image is planar, right? That means from 3D, you're coming to 2D now. That means one dimension is gone. Okay? And that is the dimension which is gone is here. Okay? So when you look at computer vision, what a camera does is when you take a picture, it is also a transformation. Exactly this transformation, exactly same. So computer graphics, robotics, image processing, they use this transformation only by changing this parameter and this parameter. So in image processing, it becomes 1 by f there. F is the focal length of the camera. So when you're taking a picture, you're converting from 3D to 2D. When you're zooming, you're doing from 3D to 4D. But the transformation is the same. Okay? So this is, it is used widely everywhere. And it's very important that you understand where it comes from and why it is like this. Okay? It's very easy to derive it. So rotation transformation, please derive it yourself, okay, after you go back today. Geometrically drew this. This figure, just geometrically do it, write down the equation, get this. Then for homogeneous transformation, you can again draw it like this, write the matrix equation and get your 4D parameters. Okay? So once you understand the geometry of this, it's very easy. Robotics has nothing more. Okay? But if you don't understand this, then it's the moment you get 10 matrices, you'll be all confused. There are 10 matrices, which one is going where? But once you understand where this came from and what is this, yeah, it's very, very easy. It can have 10 links, 20 links, it doesn't matter. Okay? So it's very important that you understand the basic geometry of what's going on. And it's in the real world, right? This is also applied in computer vision, in computer graphics, etc., etc. Now, so it has 4 parts. This is the rotation matrix, this is the translation matrix, this is perspective, and this is scale. Okay? So this is called the homogeneous transformation matrix, and if you know this matrix, you can get away, you can do forward kinematics, inverse kinematics, whatever. There's nothing more. Okay? But you need to understand this, which is very, very easy actually. Okay. Now, we'll just do one small problem before you break for lunch. So just to clarify whatever we were talking, okay? So just to clarify, suppose we have a small example like this. So a frame B. So we have 2 frames, frame A and frame B. So frame B is rotated by 60 degrees about frame A and translated by x, y, z units, by, so let's put a number here, 1, 2, and 3. Okay. So, so frame B is rotated by 60 degrees about frame A, and then it is translated by 1, 2, 3 units in x, y direction, x, y, z directions of A. Okay. So let us understand what this says. It says that a frame B, there are 2 frames A and B. So this frame B is rotated by 60 degrees about z axis of frame A. Okay. So frame B is rotated by 60 degrees about z axis of frame A, and then it is translated by 1, 2, 3 units in the x, y, z directions of A. Okay. So the question is clear. There are 2 frames. This frame B is first rotated, then is translated. Okay. Now, if the coordinates of a point BP in frame B is given by 1, 1, 1, what is AP? Okay. I hope the question is clear. So we have 2 frames A and B. The frame B is rotated by 60 degrees about z axis of frame A. Okay. Then it is translated by 1, 2, 3 units in the x, y, z directions of A. Now, if the coordinate of a point P in frame B is given by 1, 1, 1, what is the coordinate in frame A? So we have 2 frames. So frame A and frame B. So we have 2 frames, frame A and frame B. And the frame B is here. So this is my frame A, and frame B is this one is creating trouble. Okay, let's try and do it here. Which one? This one. Achha, convert to shapes. Okay, 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 okay. Yeah. Has it gone? Okay. Okay, so this is my x, y, and z. So these are two frames A and B. This is a point P there. Okay. So these are two frames. Frame A is this one. Frame B is this one. So frame B has been rotated about z axis first by 60 degrees. Okay. Then it has been translated from here to here by distance of 1, 1, 1 unit in the x, y, and z directions. Now, if you have a point P which is expressed in frame B, so PB has been given by coordinates having 1, 1, 1. Okay. Now, I want to find what is the coordinate of this point in frame A. Okay, that is the question. So, the question was there are two frames, the frame B is rotated by 60 degrees about z axis of A, and then it is translated by 1, 2, 3 units in the x, y, z direction. Okay. So, if the coordinates of BP is given by this, then what is the coordinate in frame A? Okay. So, how do we solve this problem? It is very, very simple. All we need to do is so what we need to do is write down our homogeneous transformation matrix. So, X y z is equal to the homogeneous transformation matrix into the rotated system. Okay. So, this is my homogeneous transformation matrix. So, it is said that frame B is rotated by 60 degrees about z. So, you know what is the rotation matrix. So, the rotation matrix will be this matrix only. Okay. So, it will be this matrix only, cos minus sin, sin cos, this is the rotation about z. Okay. So, the rotation matrix will exactly be that matrix only. So, it is so this is cos 60 minus sin 60. So, it is a cos 60 minus sin 60, rotation about z. So, it is 0, 0, 1, it is sin 60, it is cos 60, and this is 0, 0. So, this part is clear. It is cos 60 minus sin 60, sin 60, cos 60, 0, 0, 1. Okay, this is the rotation matrix. This is the distance between the origins in the x, y, z directions. Okay. So, this is x direction, y direction, z direction, distance between origins. So, it has been shifted by how much units? 1, 2, 3. So, 1, 2, 3 is very clear, it comes there. This is always 0, 0, 0 in robotics perspective transformation. This is always 0, 0, 0. This is always 1. So, there is nothing to remember there. This is always 0, 0, 0, there is always 1. Okay. So, this is my rotation matrix. This is the distance between the origins. This is the coordinate in frame B, which was equal to 1, 1, 1. Okay. So, all I need to do is now just multiply this into this, I get my coordinate in reference frame. Okay. Is it clear? Okay. So, it is very, very easy actually. This matrix is very, very easy. The rotation is about z, the distance between the origins, this is always 0, 0, 0, that is always 1. Just multiply this into this, it will come back in the reference frame. This one. So, this 4 by 4, otherwise it is not dimensionally consistent. So, 1 is equal to 1 we normally write. This one, it basically means that this is 4D, it is not 3D, that is the meaning. Otherwise, because this is a 4 by 4 matrix, it will not be consistent. Okay. It has to be same here. Okay. So, it basically means that this coordinate is not changing. Okay. Okay. So, let us stop with this today. So, this is basically telling you how to convert coordinates from a reference frame which is a frame which is rotated and translated to the reference frame. Okay. So, this is all you need to know. If you know this, you can do kinematics and other things, and this is very simply actually, it is very, very simple. Okay. There is nothing complicated here. When is? Here, in computer vision, it will become 1 by f. In computer vision, which you will be seeing, when you take a picture, They use exactly the same transform, but in this case your perspective will become 1 by the focal length of the camera. Okay. In robotics it is always 0, 0, 0, always 1. Here we don't have to worry. Okay. Okay, let's stop for lunch and then we'll continue again. So most of this is given in the textbook, which we'll be giving you, plus this textbook Introduction to Robotics. So it is Introduction to Robotics by John Craig. Okay. So Introduction to Robotics by John Craig. That's the name of the textbook, which covers all this in detail. This is also, you can download free, PDF is available free for download. Okay. So you can simply download this book, and all this is given there with more examples. Okay.